Hello, I'm Gary Millette, and this is ELE-110, Electronics for Technicians 1. This is the fall of 2022, and this is topic number 12, circuits consisting of R's, L's, and C's. So our last presentation, topic number 11, talked about frequency selective components, L's and C's, or C's and L's. So what happens if we have circuits containing these frequency selective components? Well, up until this point, the only circuits that we've been studying have consisted of resistors in series or parallel, or combinations of series and parallel resistors. In topic number 11, again, we did introduce frequency selective components, and these new components were capacitors and inductors. At that time, we also showed a simple circuit with a resistor and a capacitor, and a simple circuit with a resistor and inductor. In both cases, we talked about what happens when a voltage was applied to these circuits. In these cases, we talked about a charging effect or an energizing effect when we applied a voltage to the two different types of circuits. So again, what happens if we have circuits containing R's, L's, and C's? Well, we also have said that eventually any circuit with R's and either C's or L's and a DC supply would come to a fully charged or fully energized state. We call that steady state. Either the capacitor would appear as a short when first charging or an open when fully charged, and the inductor would appear as just the opposite, open when first energized and short when fully energized. But what about the case when we apply an AC signal? This opens up an entire new range of possibilities. So recall that we introduced what is known as reactance in topic number 11 also. Now reactance, you might recall, was the opposition of a capacitor or inductor to an AC current. And it turns out that it's not quite the same as resistance. Resistance is opposition to the flow of current. Reactance is the opposition to an AC current. So both capacitors and inductors exhibit reactance to AC signals, and this reactance also varies with frequency. And we talked about the two equations back in topic number 10. So the reactance of the capacitor goes from infinity at DC, which we consider a frequency of 0 hertz, to vanishingly close to 0 at extremely high frequencies. You might recall the equation was X sub C was equal to 1 divided by 2 pi Fc. Conversely, the reactance of the inductor goes from 0 ohms at DC, again F equals 0 hertz, to infinity at extremely high frequencies. And that equation was X sub L was equal to 2 pi FL. So if one has a circuit that contains R's, L's, and C's, then the varying effect of the reactance of the L's and C's will change the circuit's response to different applied frequencies. So this effect may be exploited by clever circuit design to create circuits that react at different frequencies in specific ways. So before looking at the numerous applications of circuits known as filters, let's examine some typical simple arrangements of R's, L's, and C's, but first let's get a handle on series and parallel combinations of C's and L's. So, series and parallel capacitors. Series capacitors act like parallel resistors, since the series arrangement has the effect of increasing plate separation, hence you have less capacitance. Use the parallel resistor equations to calculate the equivalent value for series resistors. And here I show two 1 microfarad capacitors in series, and I say for this example the total capacitance or equivalent capacitance equals 1/2 of either one of those, or 0.5 microfarads. You can calculate that using the parallel resistor equation, but this time it's C1 times C2 over C1 plus C2 that gives you the total equivalent capacitance. Parallel capacitors, on the other hand, act like series resistors, since the parallel arrangement has the effect of increasing plate size, hence more capacitance. Use the series resistor equations to calculate the equivalent value for parallel capacitors. Here I have those same 1 microfarad capacitors in parallel. For this example, the total capacitance would be equal to 2 microfarads, the sum of the two values. And again, we use a similar equation to the series resistor equation. The total capacitance is C1 plus C2 plus ... plus C sub n. What about series and parallel inductors? Well, series inductors act like series resistors since the series arrangement has the effect of increasing the number of turns, hence more inductance. Use the series resistor equations to calculate the equivalent value for series inductors. Here I show two 1 microhenry inductors in series, and so for this example the total inductance is 2 microhenries, and the equation would be L total is equal to L1 plus L2 plus ... plus L sub n. Again, just like series resistors. Parallel inductors, on the other hand, act like parallel resistors since the parallel arrangement has the effect of decreasing the current through each inductor, hence less inductance since less magnetic field. Use the parallel resistor equations to calculate the equivalent value for parallel inductors. Here I have two 1 microhenry inductors in parallel, and I say for this example, L total is 0.5 microhenries, and again the equation would be L1 times L2 over L1 plus L2. So some last thoughts about inductors. Inductors can be troublesome. Since the magnetic field of an inductor may fringe beyond the physical device, especially if it is an air-wound coil, it is possible that there can be coupling between two or more inductors in close proximity. And this gives rise to problems with either series or parallel inductors. Magnetic fields can penetrate conductors, hence it is difficult to contain or shield magnetic fields. You can redirect a magnetic field, but it's very difficult to shield it. Capacitors, on the other hand, have electric fields which can be more or less contained within the capacitor. So this so-called mutual coupling effect can affect the values of inductance predicted by the examples given previously. So let's take a look at some simple RCL circuits. One of the simplest circuit is also one of the most instructive. See the circuit shown here. So we see we have a signal generator, a 1 k ohm resistor called R1, and a 1 microfarad capacitor called C1. So at low frequencies, the capacitor C1 will look like an open circuit or infinite reactance. And as a result, all the input signal will appear across C1, the output or load. At high frequencies, the capacitor C1 will look like a short circuit or zero reactance, and the output will be zero. If one plots the frequency response, that is the output versus frequency of this circuit, it is the classic low-pass filter. That is, it passes low frequency and does not pass high frequency. So using circuit maker simulation software, shown here, is a plot of the frequency response of the prior circuit. So if you take a look at this from about 1 to, well, at least 15 or 20 hertz, and that frequency is logarithmic on the bottom, it turns out the output's basically a 1. Then there's a transition period that goes all the way up to 10 kilohertz, when it turns out that now the output apparently is close to 0. So as I just pointed out, as one can see from the plot, at low frequency the output's equal to the input, output of 1, and then as frequency goes up, the output goes down towards 0. Excuse me. The rapid output transition basically happens between 10 hertz and 10 kilohertz. After 10 kilohertz, the output's basically negligible. If we did some calculations, we would discover that the value of capacitive reactance would be equal to the value of the resistor at some particular frequency, and using the voltage divider rule, we could figure out this frequency. We call this frequency the cutoff frequency. Another interesting effect we could observe about this circuit is that a phase shift exists between the input signal and the output signal. Using an oscilloscope, we can observe that at low frequencies, the two signals are in phase, while at high frequencies, they are 90 degrees out of phase. All this can be calculated if desired However, some additional theory is required. We need to introduce the concept of impedance. Impedance is a combination of reactance and resistance. A circuit that has both resistance and reactance is said to have impedance to the flow of AC. There's a whole additional lore of equations that deal with impedance. Suffice to say that these equations introduce the phase angle that occurs due to the lack of instantaneous change in voltage across a capacitor and current through an inductor when electrical energy is applied. At this point, we will not belabor these equations, but instead point out some interesting concepts concerning impedance. And I should probably mention that the basic equation for impedance, if I had a resistor and a capacitor, I would get the impedance by taking the square root of the sum of the squares. That is, I take the resistance, square it, I take the reactance and the capacitor, square it, add them together, and take their square root. That would give me the impedance of that circuit of a series resistor and capacitor. The phase angle would be given by taking the tangent of, I think it's x sub c over r. And you would find the phase angle. So if x sub c was equal to r, I'd have the inverse tangent of 1, which would be 45 degrees. So again, there's a lot of equations which you don't want to take at this point in time and fill your brains with. The phase angles introduced by capacity and inductance are 180 degrees out of phase, so the individual reactances algebraically cancel one another out. We will return to this later. So if I have a circuit that's got a capacitor and an inductor in it, it turns out the reactance from the capacitor and the reactance from the inductor actually cancel one another out. So here's the simple R and C circuit revisited. Let's take this circuit, and what we've done now is we actually have just switched the position of the resistor and the capacitor. Before the capacitor was the output and the resistor was the series component. Now the capacitor is the series component and the resistor is the output. Now we have a simple high-pass filter. Why? Because at low frequencies the capacitor acts like an open circuit and there's no output. At high frequencies the capacitor acts like a short and everything appears at the output. If I use Circuit Maker again, here's the new frequency response as plotted by Circuit Maker, just the opposite of before. This is a high-pass filter versus a low-pass filter. Notice at low frequencies nothing gets through, but above about 1 kilohertz here, everything gets through. The output's 1. Since L's and C's are the duals of one another, they act the opposite. We can change what a circuit does by interchanging these two components. If we change the capacitor in a low-pass filter circuit, go back to slide number 11 or 12, with an inductor, it becomes a high-pass filter. If we change the capacitor in a high-pass filter, slide 17, with an inductor, it will become a low-pass filter. We may also construct bandpass or bandstop filters by using both capacitors and inductors in a circuit as shown on some upcoming slides. For these types of circuits at some frequency, the value of X sub C and X sub L will cancel out and leave only the resistance of the circuit. We call this frequency resonance, and the circuit, we call this frequency resonance, and the frequency at which occurs the resonant frequency of the circuit. This effect allows us to construct bandpass and bandstop filters depending upon the output of the circuit. These types of circuits are very important in the field of electronic communications. It is the principle behind the operation of wireless communications. So here's a bandpass filter. The following simple circuit is a bandpass filter with the output across the resistor R1. At resonance, L1 and L2 cancel each other out and form a short circuit. Now again, L1 will have a reactance and C1 will have a reactance. At some frequency, they are equal to one another, and they're 180 degrees out of phase, and therefore cancel one another out. If that is the case, all the input is across the output. What frequency does that occur at? The resonant frequency is given by this equation that says F naught is equal to 1 divided by 2 pi times the square root of, in this case, I've got L1 times C1. If they're just L and C, we'd call it square root of LC. So here's the bandpass filter response. The following plot shows the frequency response of the bandpass filter that we just saw with the output across the resistor. Notice the resonant frequency of about 5 kilohertz, very close to the predicted value. The sharpness of the peak in the plot is very dependent upon the value of the resistor in the circuit because it introduces loss. Here's a new plot for R1 is equal to 10 ohms compared to what it was before, 100 ohms I believe. And the plot shows the 5 kilohertz resonant frequency even more closely, now with less loss. So this last one is a band stop filter. The following circuit with its output across R2 acts like a band rejection filter, since at resonance the series components L1 and C1 cancel one another out and form a short circuit. Again, this idea that the inductive reactance is equal to the capacitive reactance at some frequencies is extremely important for this concept. And what happens is, again, since they're 90 degrees out of phase, the two add up to 180 degrees out of phase, which actually cancel one another out. And so at some frequency, that series combination of L1 and C1 act like a short circuit. So the following plot shows the output across resistor R2 of the previous band rejection filter or band stop filter. Again, for the values of C1 and L1, this occurs at about 5 kilohertz. What do we use band rejection filters for? They're usually used to get rid of interfering signals. So, a summary of all this brief overview of circuits with R's, L's, and C's doesn't do justice to the lore of this topic. That should be DO instead of DUE, but will instead serve as an introduction to this topic. There are many calculations involving impedance that have not been presented here, but in the overall scheme of things, those calculations may be picked up later on a case-by-case basis as needed. Furthermore, at high frequencies, there are physical substitutes for resonant circuits in the form of physical structures that may be used to act as resonant circuits. It's difficult to get values of L and C that resonate up in the microwave region. These structures may be metallic microwave resonance cavities or, for instance, the two mirrors of a laser.